Yeah, thanks for the introduction. And first, good afternoon, everyone. Today, I'm going to share some of the empirical experience of applying deep learning into one of the new security space called user and entity behavior analytics. So first, a little bit introduction of myself and the company I work for. My name is Jisheng Wan. And I joined Hewlett-Packard Enterprise early this year through the Neuro acquisition, and now I'm the Senior Director of Data Science in the city office. My experience in the past decade mostly focused on applying state-of-the-art machine learning and big data technology into security. And Neuro is a 3.5-year-old startup which focuses on reinventing the enterprise security using big data and data science. And this got acquired by Aruba and HP early this year. So before we go to the details of deep learning models examples, I want to spend a little bit of time first explaining what are the security problems we try to solve through this like a UEBA solution. So these two graphs shows a clear gap in the current enterprise security market. On the left, you can see the security spending from big enterprise these days in the last 5 years increased almost doubled. But on the right graph, it shows the number of the breach increased even more than doubled during the same period of time. And remember, this does not even include any of the recent like ransomware, WannaCry, any of these like crazy attacks these days. So how does this happen? There are two main reasons. First, these days attackers are just innovating and adapting really fast. And also, on the other side, there are so many of these vulnerabilities from different operational systems or devices got discovered by those smarter attackers every day. So in addition, the enterprise defense strategy also become a little bit, the traditional enterprise defense strategy also becomes less effective. So most of the traditional security solution, what they try to do is to protect the border of the enterprise. They try to detect the attackers from outside and prevent them from entering into the enterprise. But you all know with the increased use of IoT and cloud adoptions, the border of the enterprise just becomes more and more weak. So like one easy example is if you bring your smartphone, like iPhone or Android phone, into some like Starbucks, then you found a phishing email there, and you click the link, then your phone may get compromised. Then you take your phone back into enterprise. In this case, all of the defense people deployed on the border just become useless. So then what should we do? A couple of things. First, just like most of our other consumer industries, we want to take advantage of this like advanced machine intelligence, including deep learning, when we combat with attackers. Second, also, we also need to change our mindset here. These days, for any of the big enterprise, some of the users of device being compromised is not a question of if, but a question of when. So when we design the new enterprise security solution these days, we have to take it for granted that some of the users or devices in the enterprise is just compromised. Then the goal actually is how to detect those compromised users before they make further damage in the enterprise. So now you see it's a mindset shift that rather than just focusing on detecting the attackers from outside, we also want to focus on detecting the compromised users from inside. So to sum up here, and there are 3 key points of the UEBA solution. First, it has to be driven by machine intelligence rather than human knowledge. Second, the focus of the detection should be not only just the attacker from the outside, but also the compromised user and the device from inside. So also with this shift, we also moved away from just the pure prevention, try to prevent the attackers getting to the enterprise, to some even post-infection detection. So from our current customer deployments, there are at least three security use cases this UEBA solution can help with. The first is what we call this compromised user case. All of this headline enterprise breach these days mostly started from like compromising one device inside that enterprise. So if you know the story, the breach from Sony last year, I think Target and Home Depot, just more and more these days. The second category is this malicious insider. You probably heard these days there are just more and more news about the employees leaving company with stealing of the IP or company sensitive information. And one interesting use case we recently heard from our customer is he told us there's actually a layoff with hundreds of people announced in the company. Then he noticed that he actually is the IT person. He noticed that the usage and the access, the data transfer, all of this to their internal data repository like GitHub document repository just increased about like 3x. But without this kind of solution, behavior UEBA solution, he just has no visibility about what happened there. So the third category here is what we call the negligent users. You may have heard about some DDoS attack happened last September time, which brought down about 1/3 of the internet, including like all of the large ones like CNN, Yahoo, all of this. And that attack all happened from just home users installing their camera, internet-facing camera, without changing the default password. These days it's very popular. Those home users want to put a camera inside the home, look at what their kids doing during the daytime, and they want to just watch this remotely from the internet. And but they forgot to change their password. So the attacker, in this case, just scanned the whole internet, used the default password like admin or 1234. And surprisingly, that attacker controlled the attackers. It's a group of attackers. They controlled probably over hundreds of thousands of this kind of devices over the internet. And he then just turned them into like bots and launched a big attack later. So I bet most of you probably heard the recent WannaCry ransomware. This technically is another kind of, we also consider this as negligent users. Because the patch actually has released, from Microsoft has released a couple months before this recent attack. People are just either too busy or too lazy to patch their device. So generally speaking, with the increased use of this personal and also this IoT devices in the future, we expect this kind of security gap will still remain there for quite some time. So now after we understand what is the goal of the UEBA solution, I'm going to spend a little bit of time talking about the deep learning-based solution we have built inside Nero. So there are three, because here our main focus is enterprise security. And there are three common attacking behavior we normally will observe for any of these advanced targeted attacks these days. Let's still go back to this compromised phone case. When you bring the phone back to the enterprise, your phone may not have any of the sensitive information. So in that case, the attacker actually most probably will turn your phone as a bot inside the enterprise. First thing is try to scan all of the intranet to find those servers, or repository which host sensitive information. So that's the first stage of the scanning attack. Then once they find those sensitive data or important data to the enterprise, they will move the data from a server to this kind of compromised machine they control. This is the second stage. And at the end, they have to find some way to exfiltrate the data, to send the data out to the attacker. This is what we call the exfiltration. So even the exfiltration these days is pretty tricky. Most of the, for example, some of the smart or intelligent attackers, they want to just upload, say, 1 terabyte of data within 10 minutes to some destination, especially the destination is in some foreign countries. Why? Just because it's the signal is too strong, it's too easy to be caught. So what they will do is they will first chop the data, first encrypt the data, then they chop this large data into small chunks, and also use some of the intermediate places like box or job box. It's mostly like local intermediate locations. They will send the data to those job box, and finally they will download the data from there. So you can see those most of the modern attacks, especially to big enterprise, are very well designed. That's the reason they can always succeed these days. And now let's take a look of the deep learning-based solution we have developed for detecting this kind of attacking behavior. The first example is this convolutional neural network-based anomaly detection solution. So since the convolutional neural network is most effective for image processing, so we actually found an innovative way to encode the user's daily behavior into this called multi-channel image. So if you look at these two graphs, these are just the two normal user behavior during a day of the time. And if you look at the user one, let me try to point them, this one. Yeah. So if you look at this graph, the first graph on the left top, the y-axis here represents the 24 hours of the day. And the x-axis here represents 6 minutes of the hour. So each pixel in this subgraph represents a minute of that day. And the color of that pixel represents any of this numerical number. Like in this case, actually, we monitor the data transfer volume from each user. So in this case, actually, certainly the red the color, the higher the number of the volume or bytes of the data is transferred. So in this way, we can encode each user's daily behavior across all these different protocols. So you can see from these two graphs, these are two normal users' daily behavior. It's very clear both of the users actually are 9 to 5 or 9 to 6 users. They come to office to work. But the difference here is it looks like the user 2 actually likes to have a lunch break. This is what tells us from this graph here. But the user 1 seems to be working hard in the office all the time. And we even think about try to differentiate, try to break this into more granularity subgraphs, like say, if we monitor the user, because here we just put all of the encrypted communication through SSL and HTTPS. But these days, there's just too many of the applications going there, like LinkedIn, Facebook, all of the social goes there. So if we actually break this down, some of this encrypted communication even into low levels of the application level. Say, when the user uses LinkedIn, when the user actually checks email, when the user actually uses social every day. So this kind of fingerprinting, image-based fingerprinting is we found is very discriminative for most of the enterprise users. So now, after we look at the user behavior, we can take a look of the user and the machine behavior here to compare them. So you can see from the machine behavior, you can see more of this regularity here. It's not surprising just because most of machines these days are just configured to do one or a small number of this specific work. So you can see this kind of regular patterns here. They will send some, I think in this case, this is a low volume file server in our office. It will be accessed or the data will be backed up at some frequency, but not very high volume here. And with this kind of image encoding, we can just convert each of the either user or device, like a daily behavior, into some graph. And the next thing is to build this called, you probably are familiar with this. This is the convolutional neural network we built. So the way we did this is in the training stage, if we start from the left, we collect the past 90 days of users and device this daily behavior image. And then we label them with username, date, and group information. Then we feed all of this training data into this neural network. In this case, we have only 2 layers of the convolution and the pooling. And for the feature extraction. And at the end, we actually build a fully connected layer to expand them to this like 1,024 nodes here. And also, this is like recommended by Hinton's paper before, the deep learning paper. We also do some random dropout to avoid the overfitting at the last stage. So what we expect here in the training stage is if after we feed all of this daily users behavior image into the network, and after we finish all of the training, we expect each node from this outer layer represent a unique user in the enterprise. So that's the reason the way we use to encode the user behavior into image has to be very discriminative. And after we build off this classifier as a training, then we can move to the detection or the inference stage of this. It's the same process. We train with the past 90 days of the image, then we feed with today's image. The image will go through the same neural network, and finally, we expect one of the nodes will be lit up at the end. If this node is the same user as the training data, which means that user's today's behavior is the same or similar to this user's historical behavior. So there's no anomaly detected there. But if this user happens to light up a different node in the output stage during this detection, which means that the user changed his or her behavior. So this is a way we actually detect this daily behavior change. And we always use the sliding window to take the previous day to add more and more data into the training data and retrain the classifier every day. And this actually is the infrastructure we build for the, we use Spark streaming, and TensorFlow. I think given the time limit, I'm not going to expand too much details here on this slide, but we're going to share some more experience and lessons learned about how to put, especially TensorFlow and Spark together on one, small, middle-sized cluster. So let's take a look at what kind of behavior anomaly we detected through this approach. First, this is that still the same user. In this case, this user never worked overtime, or most of the time it's within this 9.5. And after it's compromised, we found this user started sending massive data, especially using a new protocol, which is totally deviated from this user's normal behavior. And also, we can take a look of this device, IoT device case. In this case, actually, this is a real device. It's a job camera in our office. What it does, the only thing it does is to take the video, encrypt the video, and send to AWS. So you can see in the normal behavior, you only see this intensive SSL, which is encrypted data transform. And some of this NTP is the time synchronization. It does not use any other protocols. But after it's compromised and start to do the internal scanning and the data download, you can see it fill up some quite intensive data transfer in this HTTP protocol here. So we certainly expect this convolution neural network model can detect this kind of anomalies here. OK. That's the first example. Probably now, after we look at this, a couple use cases we really detected in the real-world deployments, maybe one immediate concern or doubt you have is how noisy this kind of detection is. Or in other words, how many of the false positive alerts you generate from this. The answer actually is yes, it's pretty noisy. as most of you probably can think about. I think the fundamental reason here is for any kind of this behavior anomaly detection, human beings are not like a machine, which are kind of programmed for some regular work. Human beings can change their behavior for no reason, at any time of the day, right? So there are a couple ways to address this problem or address this challenge. In our solution, we collect all kind of behavior logs to build this high-dimensional behavior vectors to represent each user. So in this case, you can see we collect the badge log, which just tells how user access the building. We collect the AD log, authentication log, which tells us how this user tries to authenticate with the internal servers. And also we collect all this kind of cloud usage log to see how the data transfer with this SaaS or cloud-based applications there. And we do detect anomaly for each of these kind of behaviors, each dimensions here. So the next thing we do actually is to aggregate all of these anomaly signals from the same user. And also we check some of the specific temporal sequence pattern before we make the final decision. So the idea here is if it's a real attack, you remember the three-step attack I just mentioned before. There's a scanning, there's internal data movement, and there's data exfiltration. So if it's a real attack, our assumption is normally we will see more than one anomaly signal from the user. And also, those signals normally happen in some kind of expected patterns, like temporal patterns. For example, in that three-stage attack, when you do the comparameter phone is used for the scanning behavior, we will see a lot of anomaly signals, like say the phone touched a lot of new server it never touched before. It tried to access a lot of more servers than what it used to do. So all of these are behavior signals we can collect and feed into these temporal sequencing models here. And since this is a temporal sequence model, and it's very natural to use this recurrent neural network. So now I just quickly explain how we encode and how we build this RNN here for this called the entity scoring model. So on the left side, you can see this is just a sequence of the events. These anomaly signals we expect to collect for a certain user. And the right columns are just the expected confidence score of detecting a real alert. These are all labeled by the security expert. So based on this sequence of the input signals. So this kind of the training data we have feed into the neural network. And to build a recurrent neural network, the first thing we need to do is call this encoding. So it's similar to most of this NLP use case. We use this called one-hot encoding. The idea each of the unique alert type or signals is represented by one signal inside these vectors, inside these 200 vectors. Since we totally have about 200 different types of the signals, and we use the 200 by one vector here. The difference I want to mention here is this called the time decay encoding. So the idea is if you see these 4 alerts, 4 signals happen for the same user, whether these 4 signals is seen within one day of the time or 1 week of the time has different meaning or different confidence for detecting a real alert. In the most of the case, the shorter of the time span, the higher the confidence of detecting a real alert. So that's the reason when we, rather than use the same weight for all of these alerts, we also take consider of this time interval between 2 consecutive alerts when we encode this. And this is more like the example how the input encoding looks like. It's rather than one for all of the standard like one-hot encoding, we actually have a lot of the floating numbers here to represent the time interval between them. So after we encode all of these input events, the next thing is to build up the this hidden layer and the output layer. Here we set the memory back to the previous 100 alerts in the sequence. And another thing I want to point out here is output scoring, because what we expect, the expected output score is a number between 0 to 100. So we here in the score layer, we actually use a vector of 100 times 1. And when we, in the training stage, we actually encode each of these numbers into a Gaussian distribution, with a mean at this labeled score inside this 100 size vector. And in the detection stage, we actually have a softmax here to convert the output layer to some probability distribution. And then we pick the maximum likelihood value out from this which is the output score is here. So this is with this kind of iron layer on top of signal, to aggregate the anomaly signals generated from the convolutional network, and also especially check some specific pattern of the, these temporal events. We finally can reduce a lot of the false positive generated from the previous layer. So since we don't have much time left, I want to quickly also go through some of the challenges we have when you build an enterprise security solution. Enterprise applications actually is much lagged behind by the consumer applications in terms of the adoption of the advanced machine learning technology. There are some native challenges when you build enterprise applications. One of them is how do you interpret or understand and interpret this called local context. Let me give you an example. When you build one consumer application, let's say image recognition for the animals to recognize the animal from the image. If the object of the animal is labeled as a dog for user A, it's pretty much a dog for user B, C, D. It may be in different language, but it's the same kind of the label. But this is not true in the enterprise world. The behavior, all of the big enterprise, they have different characteristics in terms of how their network is deployed, what's their IT policy. All of this is so-called local context. And just because of this different local context, the anomaly we try to look for actually also varies from enterprise to enterprise. So that's the reason in our solution, we first, on the left side, you can see we build this called continuous learning to keep updating this normal baseline behavior from the background data. But on the meanwhile, we also give the user the feedback, one-click feedback, false positive or true positive, to any of the alerts or signals we generated. So in that case, we take the user feedback and use some reinforcement learning to help the model quickly adapt to this kind of local context here. So another challenge we normally see when developing enterprise application is lacking of training data. The privacy concern of collecting and storing large amount of the enterprise-sensitive data just grows more and more these days. And there's a very strict policy, especially in European countries, about how much data you can collect, how long you can store the data there. So in our solution, we built this hybrid analytics framework. In the cloud, we do save, collect and save all of the labeled data in one place. But meanwhile, we also collect the customer data and their feedbacks and group them into different industry sectors. So the idea is here is the customer, this kind of local context is more shared across the companies inside the same industry sector than the other industry sectors. And in this case, when we retrain the model, we just group the data, the centralized data and also the industry data to kind of help boost the model a little bit. And this is pretty much all about my talk today. A quick sum up. We talked about what is the security challenge, security problem UEBA solution tries to solve. And we also went through some of our examples, use CNN and RN to build a solution. Finally, it's not just the deep learning. Deep learning is not all. It still needs to be built with a lot of the support around the model. So that's all.
Yep.
sorry, it's a little bit of a rush, but hopefully, any questions?
Thank you, Dr. Wang. We're at time. I'll take one question, and then I think if you can just stick around a little bit for everybody else's questions, that would be great.
Of course.
Thank you. It seemed to me like you're training convolutional neural networks or RNNs for each user, right?
Yes.
Yeah. So how expensive is it to train each neural networks in real time and then generate alerts in real time?
No, actually, it's a one neural network for all of the users together because the output layer actually has the one node representing each user in your enterprise. So the training actually can take quite some time depending on the size of the company. We have some deployments with over hundreds of thousands of the customers. And also depending on the training period, how many days of the historical data you take. So yeah, the first training can take some time. That's the reason we actually recently looked into some incremental training. So try to avoid retrain the model with all historical data for every day is like incremental. So we have some work also going on there.